Okay, I guess I will just go over the rules once. We just have 1 minute left till we start this session. So hello everyone. Welcome to IVS-Student Conference 2021. My name is Rajashree Konar. I am a student of Professor Daniel Nassim, and I'm from part of the BIU team. Today we have this Nanoelectronics and Spintronics oral session starting from 9:30. So just to be clear, I guess I sent you all the email that the oral presentation should be exactly of 15 minutes so that you have 5 more minutes left for question and answers. And we have 2 speakers in this panel right now. First speaker is Eva Webraite Aderet from
Tel Aviv University.
From Tel Aviv University, and she will be presenting soft organic neural interface for recording and stimulating the intact retina. And yes, it's time. The stage is yours. You have our undivided attention. Please go ahead.
Okay. Hello, everyone. My name is Eva Webraite Aderet. As I was presented, I'm from Tel Aviv University and doing my PhD research at Tel Aviv University under supervision of Professor El Hanin. And today I'm going to present you part of my project. I hope it won't be too messy and you will understand. And if not, I will be happy to answer your questions at the end of the session. So the topic is soft organic neural interface for recording and stimulate in intact retina inside the eye. I'm going to give you a brief introduction into neural recording, neural stimulation. Then I will talk about why do we need soft neural interface and finish the introduction with why specifically retina. Then I will present the results and finally conclude and leave time for the questions and discussion. So first I would like to start with the introduction of evolution of neurostimulation or neural recording. And actually it dates back more than 70 years ago when Delgado, you can see in the picture on the left, did his experiments with bulls. He implanted big giant electrodes in the bull's brain and let them run. The ball ran towards him, and right at the spot when the bull was close to the Delgado, he pressed the stimulating button. Gladly, it worked and the bull stopped. So experiments back then were pretty exciting, maybe crucial and crude and whatnot, but that's what it was in the past. And the electrodes were big and hard and not as sophisticated. And over the years, the electrodes evolved. They became more sophisticated, smaller, higher density. And now also the researchers are looking for creating soft electronics and also to make them with 2 or at least 2 functions, for example, stimulation and recording. So why soft? Why soft? As we know, neural tissue, brain, retina in particular, is very soft and delicate tissue, and their elastic modulus is between hundreds of pascals to a few kilopascals. And gold standard electrodes are usually made of silicon, titanium, which are very hard and rigid materials, and that can cause huge tissue electrode mismatch, and that would in turn end in tissue scarring, glia formation, and then at the end it would cause also electrode degradation and failure. That's why researchers are looking in the middle, looking for materials that could be used for stimulating or recording and would be more soft and closer to the brain tissue. And now why retina? Retina is one of the most important organs for us probably to function properly, because if we don't see well, then the quality of life is also going down. So quickly, I will remind you how the vision works. So the light goes through the eye to the back of it where the retina is, and then it passes all the retina layers, all the cells here in the middle, and then photoreceptors, this layer, it converts the light into neural signal and passes the signal to other cells, and it goes to the brain, and we see. Unfortunately, there are diseases that cause these cells to die, to degenerate, and the light passes through, but there is no signal that goes towards the other cells and towards the brain. That's why people don't see. And it's really sad because many people around the world suffer from age-related macular degeneration or retinitis pigmentosa, and they lose vision and their life is impaired basically. So probably one of the only solutions to resolve this is to create artificial photoreceptors, artificial electrodes that would stimulate these cells. Or there are other parts, but let's say we're talking about this part. So right now we have several retinal prostheses that are in commercial use, that are in clinical trials, and they're really amazing. Most of them are based on rigid materials, and their one function is to stimulate the retina. My research and what I'm asking is, we don't really know how the retina behaves when it's inside the eye, because most of the test performed for the prosthesis is done when they take out the retina from the eye and place on the electrodes or something like that. And we don't know if it's acting the same inside the eye. And that's why it's important to have closed loop or bidirectional electrodes so that you could record and stimulate and see what's happening and adjust the stimulation parameters in there at the moment. So my project is looking to create soft electrode for neural stimulation or recording, or hopefully both at the same time. And I'm using soft material, polyurethane, as a substrate, which is soft, elastic, it's biocompatible and stable. For recording, I'm using carbon ink, which has great impedance, low impedance, and morphology gives us, we can make small electrodes, but they will have high surface area. And for stimulating part, we're using simply pigments that we found to put in a specific arrangement that absorb light, and they give electric charge that can stimulate the retina. So what did we do? We first developed electrodes with simple and straightforward procedure, screen printing. Then we want to test if these electrodes are good, if they're working properly. First, we are calling it's either 2D configuration or ex vivo, when we take the retina and place on the electrodes and record. And then we want to place the electrode inside the eye and record, stimulate, record, and see if these two experiments, they correlate, if the results are similar. And final goal, we didn't do it yet, but final goal is to do the study in vivo, in living animal. And also we would like to correlate the data from the eye to what the brain sees. So we managed to fabricate multi-electrode arrays for 2D experiments with 60 electrodes. And also we made probes that we call soft carbon probes that initially we intended for brain recording, but I used them for placing inside the eye and recording from the retina when it's inside the eye. So this is the first basic experiment I did experiments on chicken embryos. So we take egg, we take out the chicken, we take out the eye, and from the eye we take out the retina, place it on the multi-electrode array. In this case, we did comparison of our fabricated soft electrode to gold standard titanium electrodes. And we recorded, and we indeed see very good results. The electrodes are working, and the signal to noise ratio is high, and we're very happy. So we expect to see good results also inside the eye. But before that, we wanted to see the stimulation as well, if we can stimulate and record simultaneously. At this point, we didn't have the pigments on our multi-electrode arrays, but there's part of retina that is sensitive to blue light. So we tried that. And we also recorded on our MIAs and also on the standard commercial MIAs. And we see that we can stimulate and record the responses to light. The results here look really amazing because the amplitude is high and the signals are very well distinguished, while here the amplitude is lower and it's much higher frequency. But here I can't say many things that it's that our electrode is much better than the standard, because I did just few experiments to see that it's working. But we see that it's working, and we moved on to the next step. We deposited pigments on our multi-electrode array. Here you can see our soft MIA, the gold stripes and pigments in the middle, the circles. Then we placed again the retina and shined this time red light, 660 nanometers, and recorded the retinal response. And here in this on the right, you can see the direct responses to light stimulation. So, and why I'm showing here several graphs is that we can also confirm that this is direct response to stimulation, because the signal is propagating at a specific speed. So this is one of the confirmation. And then the next step was to place the probe already, the soft carbon probe inside the eye. First, it's not easy task, but here you can see the eye cup of the chicken embryo. I cut the lens out, took out the vitreous, and then I placed with micromanipulator the soft probe and laid gently on the retina, slightly pressing, but not too much, not to damage the retina. And I tried to record. First, I wanted to record spontaneous activity and to see if we can see the same as we see in 2D configuration. And indeed, we managed to record. Some of the recordings show bad signal to noise ratio. It's very hard to see, for example, or to say that this is the signal. But since I know how the signal looks like, I know that this is the signal, just the signal to noise ratio is very bad. But also we managed to record some really good activity, like here or like here, with high amplitudes and long activity. So this was very promising. And then the next step was to shine light and say that, yes, we can stimulate. So at this moment, we didn't have the pigments yet deposited on our soft probe. So we again used the blue light stimulation. We shined blue light at various durations, 5 seconds, 10 seconds, also 20, 30, 60 seconds. And we tried to record the response of the retina. We did record, you can see here the raster plot, and here's the signal shape clustered. But I want to say that it's really not an easy task, because the connection interface between the electrode and the retina is not always like sealed when it's in 2D configuration. And that's why the signal doesn't look as pretty as in other configuration, but we did manage to record. And this gives us the reason to look for ways how to improve the interface, let's say press with something or glue with something. So it gives us like one more task to create something else. But we managed to record with soft electrodes. So this, I would like to conclude with it, that we did initial testing. We compared 2D configuration with, let's say, 3D configuration inside the eye and when the retina is explanted. And we managed to record both spontaneous activity of the retina and also to stimulate and record the responses. Next step is to place, let's say, electrode inside the eye and on the brain to stimulate with light and record both inside the eye and in the brain, and see if in both cases it's working and the signal is actually going to towards the brain. Also, one more thing is to deposit the pigments on the soft probe and stimulate with red light inside the eye. it might be much more complicated, but we'll try. And to look for adhesion methods, and finally to test it inside living animals. So I would like to thank my supervisor, Professor Yael Hanin, our electrode engineer, lab engineer, Moshe David Pur, and Eric Daniel Glavaki, who is responsible for the pigment development, and also our colleagues that were working together. And that's it. Thank you very much. I'm happy to hear your comments, questions, anything.
Thank you so much. It was wonderful talk. And the floor is open for questions. If anyone has any questions, please go ahead.
If no one asks, I have a question. It's a question from someone who is not an expert, but from what I understand, the eye inside is full kind of a transparent jelly, the human eye. Am I correct?
In the eye, there is a vitreous, usually.
Yes.
That is transparent jelly.
Right. So when you put your electrode, you're not kind of, how do you put the electrode without the jelly coming out or without making damage at that point?
So in this case, I'm taking the jelly out because if I'm not gonna take it out, I'm not gonna reach the retina because it's really sealed to it. And actually, when you try to take the jelly out, it's actually a little bit stuck to the retina. So if you're not careful enough, you can take just the retina together with the jelly. And it also depends on the maturation of the animal that you're doing it with. Sometimes it's very easy to take out the jelly, sometimes it's not. Also, if somebody is looking for what to develop, there's no artificial jelly, no artificial vitreous. Usually when they do surgeries for people and place the electrodes inside the eye, they take out all that liquid, all that jelly, and they fill it with gas.
Wow, because the eye collapses, no, when you take the vitreous out?
Exactly.
So how do you keep it inflated, so to speak? You pass gas at the same time?
So in my experiments, I fill it with the solution. It's filled with solution and it holds the place. And I also developed some kind of like a cup that I put the retina in the eye inside in the cup, and it holds the shape. It doesn't collapse. But in surgeries, they usually fill it with gas and it holds the shape of the eye. And over time, it's automatically by itself fills up with the solution from the what it comes from the all kind of layers.
So you mean it regenerates?
Mm-hmm. Yeah.
Wow.
I don't know. I'm not sure in how what's the duration of that filling up, but that's how they're doing the surgeries.
Okay.
Thank you.
Any other question? No, I have one actually. Okay. You said that you used polyurethane in your experiment because it's biocompatible. Is there any other polymer you have in mind that can do the same thing like you use polyurethane?
There are like not several. There are actually many soft films like gels. Many people are using PDMS for research, but the PDMS is not suitable for if you want to make thin device. Okay. Then there is polyamide that many researchers are using it for the electronics, Pyrylene C. There are several films. It depends what you're aiming for and what the thickness you want it to be and how soft or how rigid you want it to be, because it also depends on the thickness of the film.
Thank you.
So save your eyes.
I think I am too late.
No, this is different, but still be careful.
Thank you. Thank you so much.
Hope you enjoyed.
I have one comment, Eva.
Okay.
People also use the P.PSS organic semiconductor to do the recording of brain activity.
Yes, yes. So we're coating, for example, our electrodes with P dot. It gives much higher capacitance. It increases the capacitance of the electrodes, and the recordings are better. Probably almost every research is using P dot for improving electrodes. It seems like it, and P dot PSS also shows very, very good results.
Thank you so much for your talk. I
Thank
guess
you,
we move
everyone.
on to the next speaker. Let me make you co-host. So Daniel, can you hear me properly?
Yes,
Okay.
yes.
I made you co-host, so you can share your screen now.
Can you see it?
We see now. It's still in the presentation. Now it's full screen. Okay. So I want, yes. So let me introduce our next speaker from Technion, Daniel Nikiforov. The floor is yours, and you have our undivided attention. Please go ahead.
Thank you, Rajashree, for the introduction. So I'm going to talk in this presentation about the magnetoresistance experiments in P.PSS thin films. P.PSS is a heavy dope P-type organic semiconductor, which is composed of two polymers, an whole charge carrier P dot and an electron acceptor PSS. In particular, in this talk, I will focus on magnetoresistance mechanism that originates due to electron spin polarization in a physical system that has on-site Coulomb correlation. Coulomb correlations that split the electronic energy levels. This is the outline. First, I will talk about the spin polarization mechanism. Then I will show you the magnetoresistance experimental results in the P.PSS. And finally, I will draw the main conclusion about the Coulomb correlation energy within the P.PSS films. Let's start with the spin polarization. This scheme shows schematically the localized electronic energy levels. Let me switch on the pointer. The localized electronic energy levels along the x direction, and the y-axis here is the energy. This dashed green line represents the Fermi level, and this green strip represents thermal energy. Let's consider hopping between two sites I with j. The red lines here represent the electronic wave functions. The hopping probability will be proportional to I divided by delta E squared, where delta E is the energy difference between these two sides, and I is the resonant overlap integral between these two wave functions. This relation is under the assumption of small I in compared to delta E. Now I want to hop for a moment to the experimental results. In this figure, you can see the planar conductance in P.PSS thin film is a function of temperature. The temperature here is in the power of minus 1/3. And here you can see the temperature in normal units. As you can see, at low temperature, the conductance follows the mode variable range hopping conduction in 2 dimensions. 1/3 here is related to hopping conduction in 2 dimensions, and the T0 coefficient is quite small. I will use this T0 coefficient in the conclusion section. Let's continue. Now I want to add the Coulomb correlation energy to the system. It will split the energetic energy levels of the system by U And now I want to explain why we actually expect to see this Coulomb correlation to take place in PDOT-PSS films. This scheme represents, okay, on this scheme, the planar PDOT segments are represented by yellow sheets and PSS polymer by green lines. It has been shown that within solid film, the PDOT tends to form nanocrystalline regions that are embedded in PSS matrix. And within the polycrystalline regions, the PDOT segments are pi-pi stacked. Then, if we envision the hopping conduction as a hopping between these nanocrystalline domains, which are actually charged, then we can expect from the Coulomb correlation to take place in the system. Now let's continue. And I want to show you the 4 possible scenarios of hopping in this physical system. The first one is from singly occupied to unoccupied energy level. The next one is between 2 singly occupied energy levels. And the last one, the next is between doubly and unoccupied. And the last between doubly and singly occupied energy level. Now, if we add a magnetic field into the system, it will partially polarize the spin electrons that are in singly occupied energy levels. And if the magnetic field is large enough, it will fully polarize the electronic spins. As a consequence, the hopping between 2 singly occupied energy levels will be blocked by the Pauli exclusion principle. In addition, the hopping event between doubly and unoccupied energy levels is related to that one by detailed balance. Then in steady state, this hopping will also disappear. Kuroba and Kamimura have developed this magnetoresistance mechanism, and on this figure you can see the calculated magnetoresistance response due to spin polarization. It causes positive magnetoresistance, and then at some critical magnetic field, the magnetoresistance gets saturated. This saturation is a fingerprint on this magnetoresistance response. Additional important feature of this model is that the Coulomb correlation must be large enough in compared to the thermal energy. Kuroba and Kamimura have set the minimal Coulomb correlation, which will occur to this effect. Here, T is the actual temperature of the sample, and T0 is the same T0 from the mode variable range hopping relation. Okay. Now let's proceed to the experimental results. In this figure, you can see the typical device that we use in our experiment. This is glass substrate with 4 gold electrons, and this bluish strip is the PDOT-PSS film. Its thickness, the thickness of the film on the picture is 200 nanometers, and the channel length is 1 millimeter. And in this figure, you can see the recorded change in conductance of the film as a function of magnetic field at 25 Kelvin. We measure the conductance in two different configurations of the direction of magnetic field relative to the field. The first one is when the magnetic field is perpendicular to the field, and the second when the magnetic field is parallel to it. As you can see, the magnetoconductance is anisotropic. In this figure, you can see additional magnetoresistance measurements at different temperatures. At high temperature, the change in conductance is positive and anisotropic, and as we cool the sample down, it turns to be negative, and at the lowest temperature, we see sign of saturation of the magnetoconductance. Okay, we assume that the magnetoconductance have two contributions. The first one is anisotropic and the second isotropic. We explain the anisotropic contribution by the weak localization effect. I am not going to talk about this effect. If you're interested, you can follow this paper. And the second one is explained by the spin polarization effect. Now, first we fit the anisotropic component with the weak localization, and then we subtract it from the experimental data. In the next slide, I will show you the isotropic magnetoconductance only. Here it is. With decreasing temperature, the amplitude of magnetoconductance increases, and at the lowest temperature implemented in the experiment, we can see a sign of magnetoconductance saturation. Just a moment. The dashed black lines are the fits to theoretical model. However, we couldn't explain the experimental results with the spin polarization mechanism only. We had to add two additional magnetoresistance mechanisms that take place in the Hoping conduction. The first one is quantum interference in Hoping, which yields negative and linear magnetoresistance response, and the second one is the wave function shrinkage that yields quadratic behavior. In this figure, you can see the same data from this figure recorded at 1.8 Kelvin, but in addition to it, we plot here the contribution of the spin polarization effect. And as you can see, it is already saturated at magnetic fields above 11 Tesla. Let's continue to the conclusions. So I hope I have convinced you that we have measured magnetoconductance effect that originates from spin polarization in the system, and that we have seen magnetoconductance saturation due to full spin polarization. Now, if so, then we can evaluate or estimate the minimal Coulomb correlation energy in period PSS nanocrystals. We have measured these values in our experiment, and then we can get this 2 milli-electron-volt for the Coulomb correlation. With this, I want to finish. Thank you for your attention, and I will be happy to answer your questions.
Thank you. Thank you so much, Daniel. It was a very interesting talk. You finished a couple of minutes early, and so the floor is open for questions, if anyone has any. No questions?
So, if no one asks, can I?
Yes, please.
Okay, good. So thank you for your talk. It was very interesting. I just have a question about your deposition. You said you deposited P dot on substrate, which was glass substrate, right?
Yes, yes, it is.
Can I ask just what was the method of the deposition? Yes, with the electrodes.
We are just spin coat the film on the glass and then clean where we don't need the P dot. It is spin coating. Yeah.
Okay, okay. Thank you.
Okay. Any other questions? No?
An interesting point, maybe, and continue your question. So, if you noted, the film is 200 millimeter thick, and we measure variable range hopping in 2 dimensions. So, how is it possible? It turns out that high conductivity grade P.PSS, let me show you. This is in this slide. It turns out that P.PSS originates in nanocrystalline domains, but in addition, when you spin coat it, it has a layered structure with periodicity of about 3 nanometers. Then the 2-dimensional hopping is within these layers that are really thin.
I have a question. Like you said that you did these magnetoresistance measurements in P.PSS. Do you think this particular mechanism can be studied in case of 2D materials? I don't know. I'm not familiar with the field. I just want to know if you can. Like say MOS2 or WS2, something like this, 2D materials and something.
Yeah, kind of magnetoresistance experiments are really universal tool to learn about the physical properties of the materials. So definitely yes.
Okay.
And in particular, if you want to see the spin polarization effect, you should have this on-site Coulomb correlation.
Okay. Okay. Thank you. Any other questions? No? Okay. I guess we can conclude our session. Thank you, both of you, Daniel and Eva, for your wonderful talks. Please remember, we have a break right now at 10:10, and from 10:20, we have Professor Sir Richard Friend. Please attend his talk and see you all in that other Zoom link. Thank you.
Thank you.